trapezoids and kites are not parallelograms. Okay? Trapezoids and kites fall under the other portion of, they're still, where we have what are called quadrilaterals. And then it became the parallelograms. And these would be non. And then we have the non-parallelograms. So what we're looking at today then will be the non-parallelogram part. The non-parallelograms wind up being what we call trapezoids and kites. Okay? Parallelograms we've done over the past couple of weeks. You have rectangles, rhombuses, and squares. We have all those properties that we've gone through those over and over and over again. Today we'll talk about trapezoid and kites. Within a trapezoid, there's also isosceles trapezoid. So these are the last three shapes. They've got some pretty simple properties to them, and we'll go from there. Okay. First thing we'll look at then is trapezoid. Trapezoid is going to be quadrilateral, which means it has four sides. Bless you. Wait for the second one. It has the four sides just like all the other quadrilaterals, but it only has one set of parallel sides. Okay. So, well, let's do trapezoid. Has one set. And that's basically the only definition that it has. Okay. Yeah. Trapezoid has one set of parallel sides. Okay. It doesn't necessarily have any congruent parts to it. One thing it does have, though, is if you think about the sides that connect where it's parallel, these parts here, usually we call these parts legs. We usually call those parts legs, and the angles on the legs, those two angles will always be supplementary. Because if you think about it, they're consecutive interior. So these angles here and here will be supplementary. These two angles will be different, but they'll also be supplementary. So each set are here and here. It doesn't mean that they're congruent. All four of those angles could be different. All four of them could be different. The other one is the one that you're probably more familiar with, the one you probably saw, the one you see you find, and that's the isosceles trapezoid. The isosceles trapezoid The isosceles trapezoid still has one set of parallel sides, but it has congruent legs. It has congruent legs. And it kind of stems from the idea of isosceles triangles. When you have isosceles triangles, you've got two congruent legs. Remember, the legs always looked at the congruent base angles? It's the same idea with the isosceles trapezoid then. If these guys are congruent, that means that the angles that they're looking at are also congruent. So what we say, instead of just saying one set of base angles congruent, we'll say that then they have two sets of base angles congruent. And correct me if I'm wrong, I think most of you guys have seen this picture before, and you probably all work with it. It's pretty standardized. Standard stuff as you go back to it. And really the only other thing that, you'll see with a trapezoid is something called the mid-segment. We worked with mid-segments before. Remember what the mid-segment was? I think it was, chapter 5 we did that? All right, if it's the middle of the segment, what would we call the middle of the segment? Do you remember what that's called? What was the middle of the segment called? The midpoint. So, so again, these guys have mid-segments. So you have a mid-segment of a trapezoid. Mid-segment's a trapezoid. It doesn't have to be an isosceles trapezoid for this to work. It still has one. It still connects midpoints. It connects the midpoints of the legs. And it's still parallel to the bases. Yeah. Yes, it could be. When it's an isosceles, then you'll have those four sections be all the same. Okay. The other thing I was going to say is that it's always going to also be parallel to the other two bases, just like it was in a triangle. Okay. So those three parts become parallel. And quite honestly, the craziest thing you wind up then with, the craziest thing you wind up with is a bunch of congruent angles because of parallel lines and transverses. Other than that, you guys have all worked with mid-segments. Mid-segment is equal to half the sum of the bases. It's the average of the two. Remember when you're finding an average, it's basically add up however many there are and cut it in half, or however many there are. In this case, there's two bases, the top and bottom, wherever you have it put out, written up like, and that's that. Pretty simple. Pretty simple. There's your trapezoids. Real tough. That's, and that's kind of what we get at. So if that's a mid-segment, let's find the value. Oh, I got to pull it up for you. Sorry.
X is 6.
So what we want to do is try to solve for the value of x. Now, when we do this, just like we have in the past, let's erase this out here. Give me 1 second. Write it down. Now, when we did this before, instead of taking half of something, what was the other way we wrote out those formulas whenever we had halves? How do you undo multiplying by half? You multiply by its reciprocal. Well, 1/2 is 1/2. What's reciprocal? There you go. Or we would write it like this: you double the mid-segment, and it equals the sum of the bases. The bases, base 1, base 2, doesn't matter which one's which. So when I'm looking at one like this, we have that mid-segment, which is the x plus 2, and the sum of the other two bases, the 4x minus 10 and the 8. So we write out what we know. The mid-segment is half the base of the base. So if I start filling in what we know, here's your mid-segment. And this is an example of taking half of something that's going to work out cleanly because, well, negative 10 plus 8 is negative 2. And what I'm saying, what I mean by that is when I'm looking at the halves going into that parentheses, into that term, half of 4 and half of 2 is easy to worry about. I don't have to worry about multiplying the other side by 2 because we can do that. Okay. What's half of 4? It's half of 2. So we're going to get x plus 2 is 2x minus 1. Once again, like we've been doing all along, the algebra stuff we've been working out, guys, it's not super complex. Subtract the 1x, add the 1. You get 3. Pretty straightforward. Try another one. You guys take a second to do this one. Please and thank you. Anyway, go back out and rewrite what you have. You've got your mid-segment. It's half the other two parts. Okay. And you'll notice again, it works out real clean because the stuff in the parentheses are both even. And let's see, so you get half of 6x and half of 6, so 2x and 10 is 3x and 3. Move the 2x, move the 3. Pretty fast. Excuse me. If you got real crazy, you can easily put this stuff together and make sure it does work. 14 and 10 is 24. 7 times 6 is the 62. I'm sorry, 42. Subtract the 12 and you get 30. Now watch what happens. From 30 to 24, do you go up or down? How much? 6. What's 6 less than 24? 18. Okay. Remember when we did that stuff with midpoints? Find the missing endpoint. You count going back and forth. The same basic principle here, guys. The same stuff we did when it was 88 degrees out versus 8 degrees out. Kites. Kites are a little bit different. I have never been able to draw one cleanly to save my life. Ooh. Skip it. I didn't save it. Nuts. There we go. Kites. It flies in. Shut up. I tried really hard on that. I was laughing when I figured that out. All right. So, I'm easily amused, in case you guys didn't know. Kites. Properties of kites are the easiest way to draw a kite is to do a plus sign or a lowercase t, and just connect the dots. Like that. I'm not very good at drawing. That's your best way of doing it. What a kite has, a kite is basically, if you want to think of it this way, it's two isosceles triangles that share a same base. So when you have an isosceles triangle, you've got congruent legs, like that. So isosceles triangles, it's two isosceles triangles that share the same base, and kites then have two diagonals. The diagonals of the kites are always perpendicular. Okay. And so let's see here, let's list out kites. Two sets of non-opposite sides congruent. It's got perpendicular diagonals. Now, this is where it gets kind of weird. When you have an isosceles triangle, let's go back and just cover this up. What angles are going to be the same in that? Well, yeah, the right angles, yeah, I can do that. Remember the base angles would be the same? So these parts here would be the same. Now, it works the same way on the other one, on the other part. Oops. If I go that direction, I get those other two sets of base angles being the same. These two. Now, if you remember, whenever you add two things together that equal the same, won't the sum be the same? Yeah. So what we say then is, when you have a kite, the angles that are between the two different sets of congruent legs will always be congruent. Sarah? No. No, not because they're not parallel. Right? Because it's not parallel. If they were parallel, yeah, we'd have to have that. In this case, excuse me. So what we say then is the angles between the two different sides are congruent. So these two angles will always be the same. It doesn't mean that that diagonal bisects it or anything. It just means that those two angles will wind up being the same. So far, so good? Now, the last little bit of this is you go back into congruent triangles. If I say that this is reflexive, these two triangles become congruent. Okay? You wind up with angle, angle, side, which then means that this angle here and this angle here is the same. It means that these two parts are the same. And go in the other direction, these angles down here are also the same. So the diagonals bisect. How do you want to say that? They bisect the angles between congruent sides. Okay? So the diagonals bisect the angles between the congruent sides. And the diagonal between the congruent angles is also bisected. It's kind of a mess. The kites, for being just something not too crazy, they have a lot of properties. And what was weird when I was looking at the stuff that's in this textbook is that the textbook doesn't go through and list out all of these properties. The textbook is making the assumption that you guys remember everything about congruent triangles and isosceles triangles to come up with these rules. So that's why I wanted to make sure I wrote these out for you so you can see it. Another way to think of it is if you have a good picture of it, if you get a good picture of it, yeah, one, these two, 4 right angles.
Don't do it for me.
Nice. I thought you had a question or you had to make another statement. Okay. We're not having a good day today, Josh? Okay. Then let's just be quiet for the rest of the period. We'll deal with it. Josh, I really need you to stop tackling that. This is not a difficult thing to do. Okay? I know you really hate the authority that I have, but the fact of the defiance, it's sucking the life out of everything else. Okay? Those two get it. These two here. And don't forget the angle. And the reason all this works is because of all the different properties of congruent triangles. And that's where all this stuff stems from. So it's not that it's going to be difficult. And quite honestly, as you go through the problems and you start looking at them, you're going to pick up on it real quick. Because with kites, a lot of the stuff can be taken from the diagram. And they don't really give you too much at once to make you have to work through all of it. You'll notice that I think the worst case scenario is you'll see how you've got 4 right triangles built out of that. You might have to do a Pythagorean theorem for one of the little bits there. That's really the worst that it gets because when we did this stuff in a second semester course, it was really kind of how you can relate this back to right triangle trigonometry. You can build so much stuff out of it. But by then putting it in first semester, they really go easy on you as far as how this stuff works. Let's look at some examples. Take a second or two and figure those out, please. Also try to make sure you remember the sum of the interior and some of the figures. With this having 4 sides, what's the sum of the interior? What was the sum of the interior for everything that has 4 sides? 60. You don't need a calculator for that first one. Because isn't it K the angle between the 2 different sides?
Oh, we're just finding K.
Yeah. Gotcha. So what would K be in the first one? Right. Right. The other one, yeah, you might need a calculator, but you might not need it. What's 50 and 60? 110. So if the whole thing is 360, back out the 110, what do both these have to be? 25. So it's the idea that there's a lot of background going on to it. It's not that the actual math part of it is going to be solved. The math part's pretty easy. Right? Yeah. What changes here? Yeah, that's fine.
It's going to be 55.
once again, we take this, the properties and things like that, and we relate it back to the algebra, because that's kind of what we always seem to do. That 2x and the 111 are the angles that are between the two different sides that are congruent, which means they have to be equal. Was 55.5? What would what's that angle equal? It's not. It's not going to be 80 because the height only has one set of congruent angles. Okay. So what happens here is now you have to think about it. You've got 3. Well, 110 and 110 is how much? Add the 80. How much is left to get you this 360? 50. That's stupid. Don't say that. Just write it out. Don't get out ahead of yourself. Okay. Again, the math isn't tough. It just takes a while to go. Do some more mid-seconds real quick. More algebra. Please. Yeah, because you had, yeah, sorry. Because you had it, you had one angle. You don't have for some reason, you guys start thinking 160 on it, you'll see this is right now. That's also just I mean, seriously, this is not first and second grade. I'm not an elementary teacher. I shouldn't have to tell you guys to keep your hands to yourselves and leave each other alone. Okay? Couple things you can do with that first one. Notice that your bases are both numerical. What I would do is I would just figure out what the average of 10 and 44 is. By doing that, I know what the middle part has to equal. 10 and 44 is 54, right? 27. Cut it in half and you get 27. So I would say then that 2x minus 1 has to equal 27. You get 14. If you did it the long way, you're still going to get the same idea. 2x minus 1 is half of 10 and 44. Where do you say, Josh? Yeah, you can go that way. What's the yeah, that's a shortcut way of doing it. Absolutely. So what Josh is saying here is kind of thinking it the same way, thinking it numerically. When you have numbers, if you just count, a lot of times if you're counting up and down, it's a lot easier to try to do all the algebra. Going from 43 to 32, do you go up or down? You go down how many? 11. See what I'm saying? I mean, you're on the right track, though. So you went down 11. What's 11 less than 32? 21. So this one has to equal 21 in order for it to work. Okay. By doing it, think of it in terms of numbers, sometimes it's easier than writing it out algebraically. You still have to solve for x, and you're still going to get 4x equals 21, divide out by 4. Was it 5.25? If you went the long way, you know that it would be 32 equals half, bless you, you would do that. And in that case, you would double out, you wouldn't take half, you would double it, so you get 64. Subtract the 43. And we're still getting 21 equals 4x. It works the exact same way, but sometimes there's a little bit quicker route, especially if you just have numbers. And that's what we're getting at there. Showing numbers are easier to count. The answer was 5.25. Does it change if you have to throw decimals in any of this? No, try it with the decimals. Sometimes, for some reason, you guys tend to not like it when you see weird things. So I want to make sure I showed you something that looks a little bit different than what you're accustomed to. It doesn't matter which one's which. The bases are always going to be the ones that are parallel. Those will always be the bases. What do you mean for the bases? Yeah. Yeah. That's fine. That's all you're doing. You're working through that. Not really. Now, this is an example that I don't want to try to take. I don't want to take halvesies and decimals and things like that. So I'm going to multiply both sides by the 2 to get rid of it. So if you double 17.1, you get 34.2 would be 10x and 3.2. Subtract 3.2. And just so you guys, as we've been saying all along, it's going to be okay that you get decimals for some problems because it's going to happen. Right? It happens all the time. Right? Yeah. There's a couple of them I know in the homework site that are a little weird characters. So, especially you have to remember about those little tricks with the angles. And I want you guys to work on this. This actually is a really good section of this stuff. Yeah, it should have been posted, but otherwise I've got a hard copy back. I'll get you one. So what is this, 6.6? Oh, you know what? I forgot to tell you one part of it. Isosceles. Hey, real quick, real fast. On the isosceles trapezoid, I totally forgot. I always forget this one. On the isosceles trapezoid, if it's an isosceles trapezoid, the diagonals are congruent. Okay? Just for the isosceles trapezoid, the diagonals are congruent. I completely forgot about that one. Every year I always forget that. All right. I should make a note about that. Maybe I should, remember that. Might as well keep the streak running, right? So work through those, the 8 through 36. They're real quick. They're finding some angle measures. You're doing a couple of algebra problems. You got some mid-seconds thrown in there. I will say that I think it's 36 is the weird one. 36 is a little bit of a weird one, but just use the properties of a triangle. You should be all right.